of calculus is that we are looking at average rate of change and instantaneous rate of change. Okay, those are the two big things that we're going to learn how to do. And then we're also going to learn how to do different kinds of measurements that don't fit into nice geometric packages like, oh, I can find the volume of a cone, I can do the volume of a cylinder. You know, I need to know how to do the volume of a vase that I drew, okay? Or what is the volume of like my Starbucks cup, all right? Because you know, the Starbucks cups, they all have like these, they're kind of slanted, you know? So they kind of, when you think about it, look like a trapezoid, okay? And so when I draw those, I actually usually come in with one of the clear cups with tea and take a straw and I poke through the hole and say, okay, this is your axis. We're going to rotate this cup around the axis, okay? And then we're just like, okay, so we have this trapezoid. So how do we find the volume? All right. And that's what the basic part of this course is. So you're learning a lot of the fundamental rules on how does this work, okay? You're, and so a lot of this is just going to be real number crunchy. There's almost no calculator to it until we get to like optimization, related rates, a few things, some things in volume and surface area we will do with a calculator because they will be difficult integrals, okay? There's just like some that I just like, I look at and go, oh yeah, when I look at that function, I can tell you right now it's a calculator question because no way can I do that kind of problem. Most of what we do in real life can be modeled something mathematically. So how do we find where the change is, okay, that occurs for this? So when we start, at first we're looking at velocity. So if they're talking about something changing in a straight line, then average velocity is just slope, okay? So this is, so for average velocity is nothing but y2 minus y1 over, my sloppy handwriting, x2 minus x1. Or we can say f of x2 minus f of x1 over x2 minus x1, okay? A lot of times this also gets written as delta y over delta x. Okay, so that's what we're looking at. Now, when we think instantaneous, we're thinking at a split second moment in time. Okay, so you know, what speed were you going when you hit the brick? Okay, when you know, it's like you hit a brick when you're driving down the highway and it's like, oh, it made your car bump and everything. That's your instantaneous velocity, okay? So we want to look at that. There's ways that we can measure it to see whether it's slowing down or whether it's speeding up. Define instantaneous velocity as a ratio like we can with average velocity because the x's are so close, like instantaneously together, that basically delta x here is equal to 0, okay?
Okay.
Over some delta y, and that's not defined.
All right.
Does that make sense?
Yeah.
So how do we estimate that? Well, we do it as a limit, okay? And so what we're saying is when we draw a curve, let's suppose I draw like this really big curve, okay? And I want to see what is at this one particular point right here. And I'm going to draw a horizontal axis on here too. Okay. Okay. What is the instantaneous rate at that point? Well, what I do is I say, okay, let's take 2 points that I already know. So I'm going to say, let's take this point right here and this point right here. Okay. And so I'm going to call this one x1, and this is at x2, and this is at, we'll call this one x3. Okay.
Okay.
And so what I can normally do is I find the average rate of change, and that's the slope of this line. So I can look at the average rate of change here. And it's just nothing but the slope of the secant line.
Okay.
And, you know, we learned these from geometry. So this is kind of going a little bit back. You know, you were drawing all kinds of curves where you could draw a secant line. All right. But so what we're going to do is we're going to say, well, what happens to this as I move incrementally closer to my x2? So suppose I, you know, come back in here. Let's see if I can draw it different color. And I'm going to pick like half the distance here and half the distance here. So I'm going to come up. This is a point here, and this is a point here, and it comes a little bit closer. Okay. Going through there. Didn't want to do it. That was ugly. And then I'm going to keep getting closer and closer. So I'm going to do another one, and I'm going to take half this distance here and half this distance here, and I'm going to go up and find where's this point here and where's the point here. And I'm going to draw another secant line. Now I guarantee you, even though my graph is kind of crummy, I'm still under that point. Okay.
Yeah.
And so the closer and closer my secant lines come and I shrink that distance, then I get the instantaneous velocity. Okay. And so I can come back in here and I can say instantaneous velocity is nothing more than the limit, okay, as the delta x goes to 0, okay, of I was going to say f of x over delta x, okay? And so what, I'm trying to think, I don't want to write f of x, so I think I want to write my y's. So I'm going to say my delta y, okay? And then this is going to give me the derivative, okay?
Yeah.
So this is the symbol for derivative.
Okay.
And so, and I'll actually say this would be the derivative at x2. See, closer and closer. So basically, we're going in the neighborhood of that point, and we're squeezing in closer and closer and closer until we actually like right there, okay? And that takes care of it. So we're just looking at a very small, every time I was drawing these, I was halving the distance between where I was to where I wanted to go, okay? And so I can look at these things. So the top of the Tower of Pisa, I just had friends who moved to Italy. He actually retired after working for the Federal Reserve Bank for some 20, 30 years or whatever. He was their top laptop security guy. And they have moved to Italy, okay? And I'm totally jealous. They have no kids. And I'm like totally jealous because he's like living the dream, okay? Turns out his grandparents came from Italy to the United States, okay? And so I'm like super jealous. So if we wanted to see what was the instantaneous rate of change, I could go in here and use this for like the Tower of Pisa here and say, find the average velocity over the top. If I take this and I use this function right here, okay, and we wanted to find what the instantaneous velocity is at t equal to 0.7 seconds. So we're going to do it from two intervals. We're going to do 0.7 to 0.71, and we're going to use 16t squared. So now we're going, so let's see, S of 0.7 is 16 times 0.7 squared, 7.84.
Yeah.
All right, and then we want to do S of 0.705. So, and this is 7.9524, okay?
Okay.
The average velocity in here, going back to what we were doing before, it will be 7.5924 minus 7.84, and then we're going to take the difference. So that's 0.7 minus 0.7, sorry, I've got them in the wrong order. 705 minus 0.70 minus what we started out with was 7.84. The difference now is 0.0001, right? And we get exactly 22. All right.
Okay.
Now in calculus, we're going to actually come back and show everything to 3 decimal places correct on here. So typically I do everything to 4 and then I round it to 3 when we're done. Okay. So this looks pretty good, you know? So let's see, what's it going to be? So now I need to do S and I'm going to do 7 and then 3 zeros and a 5. Wow, 22. So here's how close this is. This is 22.4008. Okay.
Okay.
See how all the more exact it's getting?
Yeah.
Yep. And so what I'm going to see, let me see if I can do this. So, yep. Okay. So then we're going to come back in here. So when we talk about when we write limits, because we have to be able to do these when we look at continuity, we're going to say the limit, oh, not in pink. Ha ha. Okay. Let's grab the pencil. The limit. Okay. And basically, we're going to say as x approaches some value c, if we're saying from the right of c, we're going to put a plus sign as a subscript or superscript.
Okay.
So as x approaches c, okay, of f of x. And that's what we're going to be looking at, okay? So
Okay.
then we're also going to be so this is the limit of f of x as x approaches c from the right. Okay. The
Okay.
second one will be the limit of f of x as x approaches c from the left. And when we're doing that, we're working either the left neighborhood or the right neighborhood.
Okay.
Okay. And then the general limit is writing the limit as x approaches c of f of x. So it's saying from both, it's squeezing in. All right. So this is just the limit of f of x as x approaches. I love this, that we got a rational function to start out with. Okay. And interesting thing, but the graph's already provided. So you can see one thing. This will take you back into pre-calc. Okay. There's only
Okay.
one vertical asymptote. And there's a hole right here. See that?
Yeah.
Yep. So that must mean this guy factors. So let's see what we're going to have. So we're going to have 3x, x. So we're going to say minus 3 plus 1. And we're going to have x plus 3 and x minus 3. So when we reduce this, this is the function that we have, right? So this is what goes right here.
Yeah.
Okay. And then if we come back in and we evaluate it at the whole, so the whole happens, so x might equal to 3 is the whole. So we're going to find it at 3. And then when we evaluate this, this is 10 over 6. Is that right? Put 3 in, I get 10, put 3 in. Yep. Okay. So the domain is everything except the vertical asymptote and the x coordinate of the whole. So we go minus infinity. The vertical asymptote is at -3. Union -3 to the whole, which is 3. Union 3 to infinity. The range is going to be everything except for our horizontal asymptote, and our whole, the y coordinate. So we're looking at minus infinity to 10 over 6, union 10 over 6. By the way, in calculus, we don't care if you simplify your fractions or not. Everything is equivalent form is accepted in calculus. Yay! You got to love that, okay? Like, seriously, I never get that. That's the best part. Now, you always have to remember to write your asymptotes as x equal to or y equal to. So your vertical is x equal to -3. And that's from your denominator.
Yeah.
And your horizontal is y equal to 3. Okay. And you can do that one of, were you ever shown how to find the horizontal asymptote by doing division?
I was told how to do asymptotes with limits, I think, or something like that.
Okay. Okay. Yeah. So what you can look at is basically it's you can say that the limit as x is approaching trying to think what it is. Oh, infinity. Okay. Of 3x plus 1 over x plus 3. Okay. It's going to be, it's basically going to be the same. Okay. So it's going to be less than or equal to the limit as x approaches infinity of 3x over x. Okay. And that's going to give you 3 because you know you're going to cancel those out, right?
Yeah.
And that's how you do it. The other way you can do it is you can do synthetic division here. So I'm going to show you this real quick. And so this is 3 and 1. Drop 3 down. That's a 3. That's a -9. So that's -8. So this is 3 minus 8 over x plus 3. Okay.
Yeah.
This is the transformation form of your rational function. So what it says in here is it's shifted to the left by 3. It's vertically stretched by a factor of 8. The minus here says that's a reflection over the x-axis. And then that's your vertical shift. And that's your horizontal asymptote.
Yeah.
Okay.
Okay.
So yeah, we don't show this in our pre-calc class. We actually show this in our math 3 class. All right. So that looks really cool. So we've got 2 different things to look at today where we're talking about the limits. Okay. So we're going to look at this. So we say pre-calculus versus the calculus notation. I love this. Okay. So we've got the graph and we're going to fix the table. So as x goes to minus infinity, okay, so that means I'm going out this direction, okay, then this is going to 3, correct?
Yeah.
Okay. As x is going to infinity, the graph of f of x is going to 3 as well, going in this direction. Okay. As x approaches -3 from the graph from the right, okay. So basically this is saying, let's write this now in calculus notation. We'll write them as the limit as x goes to minus infinity. Okay, that was like really sloppy. Of f of x is 3. And the same thing over here. The limit as x goes to infinity of f of x is 3. And I think what we'll do is if you want, you can probably go through, and I've actually already talked about this limit existence theorem, and you can probably go through and do this topic 1.4 if you want, okay, by calculating it out in the table and seeing what happens as it goes from really close from the left and from the right.
Okay.
So, because it's going to be a whole. I mean, you can look at that quadratic and say, oh, it's going to factor, x minus 3 and x plus 5.